here. So basically, this is on the single degree of freedom vibrations under the force, and that force can be expressed in terms of the combination of the harmonic functions of different frequencies. Okay, the basic frequency is in integer apart. Okay, so this one. In general, this is the generic format of the force. So basically, you can see the force combining constant and cosine omega t when j equal to 1, and j is an integer here. And please, j is not the symbols for complex numbers. And here, j is an integer. So basically, this is a harmonic motion at the frequency omega. 2 omega, 3 omega, 4 omega, etc., etc. Okay, so that is the combinations. So because the system is linear, the force is linear, so we can use the superposition principle, and we can decompose the system response to. We can decompose the system response to individual terms. For example, in chapter 3, you know how to calculate response to a constant. You know how to calculate the response to cosine omega t, sine omega t. And even you know how to calculate response to cosine 2 omega t or n omega t, whatever omega. So you know those kind of detail, we simply added up the individual response, and that is the total response. Okay? So that is the concept like this. So in terms of using the different approach, using the transfer functions, that will make the things clear. So if this is the systems, and to individual input, that is the magnitude with phase angle omega d, omega 0 t, then the response will be equal to the magnitude of the input multiplied with the magnitude of the transfer function, that is the magnitude of the response. The phase angle simply is the phase angle of the input plus the phase angle of the dynamics. So that is omega 0 and plus v, okay, etc. And we have a different response, then we simply do the repeated calculations. So the total response of a system to the combination of the force like this, okay, basically that is the total response. You simply added up the whole thing together. Very straightforward. If you have done the programming on chapter 3, then very likely you simply added up the for loop in your program, and you should be able to get this one done very quickly. And I know some of you have done the programming for your homework, so give it a try. Okay, so in the time domain, the same thing can be described by this. So this is the systems, and for example, we subject to the f0 cosine omega 1t, then here is the explicit form, okay? So this is the magnitude, okay? This appeared in our test tube. And phi1, and what is phi1? Phi1 basically defined by this angle here, by this number here, okay? And again, if the input second, the type is f2 and cosine omega 2, and that's a different omega. So basically, in the similar patterns, okay, basically you can see that is a similar pattern, but with different numbers, okay? And phi2 is in terms of r2, etc. Okay. So eventually, the whole result, the system steady state response, simply is the addition of this one plus whatever, how many terms you have is simply added up together. And so combination of the input, combination of the force will be looking like this. Then if we were able to plot the response, and that will be looking like this one for demonstrations. So basically this page and the previous slides are the summary of the whole techniques. And I would say here is nothing new. Again, simply we're using the superposition to add the system information together. Okay. So another viewpoint of this one. So maybe we can take a look at a few examples, and I would say rehearsal what we have learned. So for example, the system is like this, and so basically let me rewrite. The system is the mx double dot plus cx dot plus kx. equal to f, and what is f here? The f equal to f1 sine omega t and f sine omega 1t plus f2 sine omega 3t. Okay, so here the omega 3 equal to 3 omega whatever. Let me that information. Okay. So for this one, then we can exercise. So earlier we have, let me write it up, our template in chapter 3, what we have learned is this, mx double dot plus cx dot plus x equal to f now, and say cosine omega t. So we know the steady state response can be written by the magnitude is f now divided by k, and this is k minus n omega square plus c omega square times cosine omega t minus phi, and phi equal to arctangent c omega k minus m omega square. So that is our template. Okay, I'm going to use this template and to mark it here. So right now, from here, if we use this one, then simply, or furthermore, if you like to use R, this can be expressed by delta st. My mistake. In these expressions, they shouldn't have this one, right? Sorry, my mistake. And if you like to, in terms of this form, in terms of R, 1 minus R squared plus 2 zeta R squared and delta st and cosine omega t minus phi, and phi equal to arctangent and 2 zeta R 1 minus R squared. Okay, so if you like to use this one, then basically this delta st, by definition, this one equal to f0 divided by k. Okay, so either one will be okay. So from here, you can see right now our steady state response will be equal to, again, here we utilize these decomposition and superposition. So this system response to this form, we pick up that template. So the system response to that template basically is F1, and I'm going to use the second form because that has a less writing. Okay, so the magnitude, that is a delta st. Delta st equal to magnitude of the force, which is F1 divided by k. Okay, and then here is say, let me define R1 equal to omega 1 divided by omega n. So here is R1 square plus 2 zeta R1 square. Okay? And then cosine. Sorry, here is sine. And because this is in sine, so here we take sine and omega 1t and minus phi1. And phi1, again, is the phase angle we using that template. So here the phi1 equal to arctangent 2 zeta r1, 1 minus r1 squared. Okay? So basically here, right now I'm focusing is writing up the response of the system to this force. And that is this one. If you compare to here, so in a similar way, either this is cosine or sine, we simply change the form, okay? Then for the second term, right now I'm going to write it up, the form for the second term. So right now focusing on this one, so the second term response will be like this. And that's the linear positions, linear decompositions of which superpose, plus the second term The second term again, this is delta st. Delta st in terms of template is the magnitude of the force, which is F2, and divided by spring constant K of the system. And using the same template, which means 1 minus r squared plus 2 zeta r squared. And right now for this r, I want to define as the R2 because r is the frequency ratio, and which is omega 3 divided by omega n. Okay, and then this sign is omega 3t minus 3, and let me define as the phi3. So phi3 equal to arctangent. And again, copy from the template 2 zeta r, and for this case, r equal to R2. That's it. So you can see, in terms of the calculation, you simply repeat the calculations. Repeat the calculation by using different number of the r for each term. Can you see it? So here, I would say, if you have done your homework in terms of programming, I think for the follow-up, the homework will be a little bit easier. Again, you simply add up the do loop in this form, and then by considering the different R value, then you almost done these things. Okay? So this, we exercise the force only have 2 terms. If we force have 3 terms, then we simply repeat the things. Repeat it until whatever the number of the terms we have given. Any questions? Good. Good. Very good. Is that okay? So that we can have another one.